Hi class, make sure that before you watch this short lecture, you've actually completed the following two sections from this week. I'm referring to 6.5 and 6.6. The purpose of this lecture is to give you a quick overview of next week's. So here in the assignment, you have the actual the file and also a Desmos link that we'll be using. Please open that file, and that file is going to look like this. So I'll give you a quick moment to make sure you open it. And let me explain the main idea of next week's content. So we've already seen sections 6.5, which is integration by parts. We've also seen 6.6, which is tabular integration. And the main objective of 7.1 is to evaluate integrals using several methods. Now, not every method is going to work with an integral, but only specific integrals you can actually use different methods to solve. And this may actually create a little bit of a discrepancy on the solutions. Our constants may not entirely match exactly on every single problem. So that's why I've actually inputted here at the bottom the link to Desmos so that you can graph the equation and the solution. So for the homework assignments, some of the questions are asking for you to match the answer. So you can use Desmos for that particular type of problem. And let me just quickly do a review of the two main objectives of this week. And one of them was the idea of integration by parts. Now, keep in mind that when we're talking about integration by parts, and also in this case, tabular integration, there is two values being multiplied and the actual integral. So we're talking about two functions. In this case, you could actually view that u as an f of x and the dv as an actual g of x dx. So we're looking at multiplication of functions, and if your functions are multiplying, and here's the other important portion, one differentiates to 0, both of these methods can be used. So you're looking for two functions that multiply, and then also that eventually with a couple of derivatives, you're gonna actually reach the value of 0. And then we're also assuming that you can evaluate the integrals, of course. Okay, so let's actually jump into a quick example that's gonna illustrate the topics of next week. And let me actually look at example 1. In example 1, they're asking us to use tabular integration to evaluate the integral. So what I'm gonna do is I'm just gonna actually rewrite it. So this is gonna be the integral of f of x g of x dx, and technically your f of x, it's gonna be the x to the second. Your g of x is equal to the e to the x. And remember what we said, your two functions need to be multiplying. And then as you set up the table, you're gonna put your actual function f of x and then your function g of x. And then let me use the actual, I'm not sure what color this is, but I'm going to start with the x squared. And remember that within tabular integration, you're taking derivatives of all of these. So all of these, you're taking a derivative. So in this case, you start with an x squared, then you're going to end up with the first derivative to be 2x, then 2, and then followed by 0. The second column in the table, you're going to be doing integrals. So that's gonna start with g of x, which is actually an e to the x. And then the integral of e to the x is also e to the x. The integral of it is e to the x. And you're going to continue this pattern. And remember that there is a pairing. So let me use blue for the pairing. You're pairing these functions. And the last one we don't need because technically it's going to be in this case an e to the x, so it's going to end up being a 0. And then also don't forget that there is a plus and minus, and then let me write out the final answer here. By tabular integration, we technically have, and let me rewrite this. We technically have that the integral of x squared e to the x dx is equal to the following products. And remember that you're technically multiplying these. So the first term is going to be an x squared e to the x. And then the second term is going to be the negative. So it'll be negative 2x e to the x. And then plus a 2 e to the x plus technically the constant of integration. So here is the first solution using tabular integration. And let me pause the video for a second in case you need to go back and actually check some of the work. Okay, for the second part of this video, let me actually solve the same problem, but we're going to be using integration by parts. So we're looking at this idea here of the u's and the v's. So it's a different formula, but it's still going to work. Now, remember that on integration by parts, there's a little bit of a guessing. So what I'm going to do here first is I'm going to start with the first iteration. So I'm just going to let u equal to the x squared, then the u is equal to 2x, and also v is equal to your e to the x, and then the v is equal to technically, well, e to the x. Now, this is going to be for the first iteration. So you're going to end up with, and let me just put the formula again. I'm referring to this formula. So uv minus the integral of v du. So the first portion, it's going to be your uv minus the integral of v du. It's actually going to give us the u. In this case, it's going to be an x squared. Your v, it's going to be an e to the x minus the integral of v. In this case, it's going to be an e to the x. And then the u, I'm just going to put the 2x dx. Now, remember that integration by parts technically may have more than one iteration, and you may have to repeat this process. So in this case, this is the first iteration. Let's actually do the second iteration. But on my second iteration, I'm actually looking at the resulting integral. So in this case, we're looking at this portion here. So we're going to let again u equal to, in this case, is the 2x. The u is equal to 2. And then v is equal to e to the x. And dv is equal to a e to the x. And let me just put here that we're going to be evaluating uv minus the integral of v du, which is equal to your u and the v. So it is going to be a 2x e to the x minus the integral of v, which in this case is an e to the x, and then, hold on, so du, which is a 2. Sorry, I was looking at another part. Okay, and this will be the x. So in this case, we can actually integrate this one by itself, and we don't need to do another integration by parts. You're looking at 2x e to the x minus the integral of 2e to the x is simply a 2e to the x. So as we pair up our solutions, we're going to be using, and let me use orange, this for the first part. And then the resulting integral ended up with a minus this portion. So as our final solution, let me rewrite it, that in this case, the integral of x squared e to the x dx is equal to a x squared e to the x from this part, and then your resulting, second iteration, which is technically, because we have the minus, this portion has to be a minus. So it'll be minus 2x e to the x plus 2 e to the x, and then plus the constant of integration. So in this situation, it was a lot messier to actually approach this problem by integration by parts. And let me try to fit both solutions in here to make sure that there's no errors. It was a lot messier to do it by parts. And also another portion of the problem that I wanted to point out, every time that you're doing by parts, you may end up with an integral that you may need to do by parts again. On this last one, we didn't do by parts because it was a simpler integral, but on some of the problems, it may turn out to be too much work. It may just be easier if you recognize to use tabular. The main idea is the function has to differentiate to 0, and then your other function you're able to integrate. If you satisfy these two conditions, then you may use either, but you have to make sure that one function differentiates to 0. In this case, well, as you can see, it was a little bit messier to use by parts. Some of the problems may be asking you to graph your solutions or select a specific solution. For this one, I just provided the graphs here. I also gave you the link for Desmos in case you want to check it, but that's what both of the functions are going to look like. The last portion that I wanted to leave you with is that for some of your problems, your solutions that you're obtaining may not be identical. So you may end up with a negative x, or not a negative x, sorry, a negative constant. In this case, if I would have followed the algebra, this would have been technically a negative c. But on any problem, as we're integrating, since we don't have the bounds, you could just always say plus a constant, but the constant could end up being negative. So there is a chance that another problem, if you follow all the algebra correctly, you end up with a constant that's negative or a fractional constant. Okay, that was actually it, you guys. I just wanted to give you a quick overview of next week's content, which basically is based on these two main lectures.